In 2014, a Hollywood blockbuster achieved something unprecedented in the history of cinema. It became so scientifically accurate that it led to peer-reviewed research papers, advanced our understanding of black hole visualization, and earned praise from Nobel Prize-winning physicists. Interstellar didn't just entertain audiences. It educated them about some of the most complex concepts in modern physics while maintaining such rigorous scientific accuracy that NASA uses clips from the movie in educational presentations. This wasn't an accident. Interstellar represents the culmination of an extraordinary collaboration between filmmaker Christopher Nolan and theoretical physicist Kip Thorne, who insisted that nothing in the movie would violate known physics unless absolutely necessary for the story. The result is a film where science fiction emerges from actual science, where the impossible becomes plausible through rigorous application of Einstein's theories, and where audiences experience scientifically accurate black holes, time dilation, and higher dimensional physics. Most space movies treat scientific accuracy as optional, prioritizing spectacular visuals and dramatic moments over physical realism. Ships bank in space like fighter jets, explosions create sound in vacuum, and characters travel between solar systems as easily as driving to the grocery store. But Interstellar took the opposite approach, using real physics as a constraint. That actually enhanced the storytelling rather than limiting it. The movie's commitment to scientific accuracy began with Kip Thorne's involvement as executive producer and scientific consultant. Thorne, who later won the Nobel Prize in Physics for his work on gravitational waves, insisted that the filmmakers follow what he called the science of Interstellar, a comprehensive framework ensuring that every major plot element could be justified by known or plausible physics. This scientific rigor led to breakthrough visualizations that advanced actual research. The computer-generated black hole Gargantua wasn't just visually impressive. It was so accurate that it enabled new insights into how black holes would actually appear to human observers, leading to scientific publications that cited the movie's visual effects work as contributing to our understanding of extreme gravitational lensing. The movie's depiction of time dilation near massive objects represents one of the most accurate portrayals of general relativity ever filmed. When Cooper and Brand experience 1 hour equals 7 years on Miller's planet near the black hole Gargantua, the film correctly shows how extreme gravitational fields slow the passage of time relative to distant observers, creating emotional drama directly from Einstein's equations. But Interstellar's accuracy extends far beyond black holes and relativity. The movie's portrayal of space travel, orbital mechanics, planetary environments, and even agricultural science reflects careful attention to real physics and current scientific understanding. When the Endurance rotates to create artificial gravity, when spacecraft perform gravitational slingshot maneuvers, and when explorers encounter alien worlds with realistic atmospheric compositions, the movie demonstrates that scientific accuracy can enhance rather than constrain dramatic storytelling. The film's treatment of higher dimensional physics, while necessarily speculative, remains grounded in serious theoretical frameworks developed by string theorists and cosmologists. The Tesseract sequence, where Cooper experiences time as a navigable dimension, represents a visualization of concepts from general relativity and quantum mechanics that physicists actually study, even though we lack technology to observe them directly. Perhaps most remarkably, Interstellar achieved this scientific accuracy while telling a deeply human story about love, sacrifice, and humanity's survival instincts. The movie demonstrates that audiences can handle complex physics when it serves compelling emotional narratives, challenging the assumption that scientific accuracy must be sacrificed for mainstream appeal. The movie's environmental Themes reflect realistic climate science and agricultural challenges facing Earth's future. The dust storms, crop failures, and ecosystem collapse depicted in the film represent plausible scenarios based on current understanding of climate change, soil depletion, and agricultural sustainability. Adding urgency to the space exploration narrative, Christopher Nolan's visual approach prioritized practical effects and real locations wherever possible, using actual cornfields, building rotating spacecraft sets, and filming in spectacular natural locations to ground the fantastic elements in physical reality. This commitment to practical filmmaking reinforced the scientific authenticity by making impossible scenarios feel tangible and immediate. The movie's sound design even reflects space physics accuracy by eliminating sound during space sequences, correctly showing that vacuum doesn't transmit acoustic waves. The famous no sound in space rule, violated by almost every other space movie, becomes a dramatic element that enhances tension rather than reducing it. But what makes Interstellar truly exceptional is how it uses scientific accuracy as a storytelling tool rather than an obstacle to overcome. The physics of time dilation creates emotional stakes about aging and mortality. The realism of space travel emphasizes humanity's vulnerability and courage. The accuracy of black hole physics makes the impossible seem achievable through scientific understanding. If you're fascinated by how Hollywood can get science right while telling compelling stories, subscribe and hit thumbs up. And here's a mind-bending question that connects science to storytelling. If a movie can be so scientifically accurate that it advances actual research while moving audiences to tears, what does this tell us about the relationship between scientific truth and human meaning? Comment below with your thoughts on whether accuracy enhances or constrains creative storytelling. The influence of Interstellar extends beyond entertainment into education and public science communication. Physics professors use scenes from the movie to explain relativity. NASA incorporates clips into presentations. And the film has inspired countless students to pursue careers in physics and astronomy by showing that real science can be as exciting as any fiction. The movie's legacy includes actual scientific contributions, from black hole visualization research to renewed public interest in space exploration and theoretical physics. Kip Thorne's book, The Science of Interstellar, became a bestseller, demonstrating public appetite for understanding the real physics behind fictional narratives. But Interstellar's greatest achievement might be proving that audiences hunger for scientific authenticity when it's presented through compelling human stories. The movie's success challenged Hollywood's assumption that complex science must be simplified or ignored, opening doors for more scientifically literate entertainment that respects both physics and storytelling. We're about to explore how Interstellar achieved this unprecedented balance between scientific rigor and dramatic power, examining the real physics behind every major element while understanding how accuracy enhanced rather than limited the movie's emotional impact. From the mathematics of Gargantua to the reality of time dilation, from the physics of interstellar travel to the science of higher dimensions, we'll discover why getting the science right made everything else more powerful. This isn't just about a movie. It's about the relationship between scientific truth and human storytelling, between what's possible and what's meaningful, and about how understanding real physics can make impossible dreams feel achievable. Through the power of scientific knowledge and human determination. Now, let's journey through the science of Interstellar and discover why accuracy in impossible scenarios makes the impossible seem possible. Chapter 1. Scientific Foundation. The unprecedented scientific accuracy of Interstellar began with an extraordinary decision by filmmaker Christopher Nolan to place theoretical physicist Kip Thorne at the center of the creative process, not as an afterthought consultant, but as an executive producer with veto power over any scientific elements that violated known physics. This collaboration between one of Hollywood's most visionary directors and one of the world's leading theoretical physicists created a new model for how science fiction can emerge from actual science rather than contradicting it. Kip Thorne brought unique qualifications to the project as a Nobel Prize-winning physicist whose research focuses on general relativity, black holes, and gravitational waves, precisely the phenomena that would become central to Interstellar's plot. Thorne's work with the LIGO Gravitational Wave Observatory and his pioneering research into black hole physics provided the scientific foundation that transformed what could have been another space fantasy into a rigorously grounded exploration of real physics. The collaboration began when producer Linda Obst approached Thorne about developing a scientifically accurate movie about interstellar travel and time manipulation, rather than simply using science as window dressing for dramatic scenarios. Thorne insisted on what he called the science of Interstellar, a comprehensive framework where known physics would constrain and shape the story rather than being ignored for convenience. Thorne's fundamental rule was that nothing in the movie could violate established physical laws unless absolutely necessary for the plot, and even then, any departures from known physics had to be based on serious theoretical speculation rather than pure fantasy. This constraint forced the screenwriters to find creative solutions that worked within physical reality, often leading to more interesting and innovative storytelling than conventional science fiction approaches. The development process involved extensive collaboration between Thorne and the screenwriting team, led initially by Jonathan Nolan and later by Christopher Nolan. Each major plot element underwent rigorous scientific scrutiny, with Thorne providing detailed explanations of the physics involved and suggesting modifications when story elements conflicted with physical reality. One of the most significant early decisions involved the choice of gravitational anomalies and wormholes as the primary science fiction elements, rather than invoking faster-than-light travel or other physics-violating technologies. The movie grounded its fantastic elements in general relativity phenomena that are theoretically possible, even if currently beyond human technological capability. Thorne's insistence on accuracy extended to the mathematics underlying the movie's key sequences. The gravitational anomalies affecting Earth's environment, the time dilation effects near black holes, and the orbital mechanics of spacecraft maneuvers all involved detailed calculations to ensure that what audiences saw on screen reflected what would actually happen under those physical conditions. The black hole Gargantua became a particular focus of scientific accuracy, with Thorne working closely with visual effects supervisor Paul Franklin to create the most accurate black hole visualization ever attempted in popular media. This collaboration required solving Einstein's field equations to determine exactly how light would behave in the extreme gravitational fields near a massive, rotating black hole. Thorne's scientific constraints often enhanced rather than limited the dramatic possibilities. The time dilation effects that create emotional tension between crew members aging at different rates emerged directly from Einstein's general relativity. The danger of approaching black hole event horizons reflects real physics of tidal forces and gravitational gradients. The challenges of interstellar navigation incorporate actual orbital mechanics and energy requirements. The wormhole traversal sequences required extensive consultation on general relativity and cosmology to ensure that the visual representation and physical sensations experienced by the characters would match theoretical predictions about travel through shortcuts in spacetime. Thorne worked with the visual effects team to show how light and perspective would change during wormhole passage. Dr. Thorne's involvement extended to training the actors in basic physics concepts so they could deliver scientifically accurate dialogue convincingly. Matthew McConaughey, Anne Hathaway, and other cast members received tutorials on black holes, relativity, and space travel to help them understand their characters, motivations, and the physical reality they were experiencing. The scientific accuracy requirement influenced every aspect of production design, from spacecraft architecture that reflects real engineering constraints to planetary environments based on actual exoplanet research. Production designer Guy Hendricks Diaz worked closely with Thorne to ensure that even background details reflected plausible future technology and realistic space environments. Thorne's educational background and communication skills proved essential for translating complex physics into accessible explanations that could be incorporated into dialogue and visual storytelling. His ability to explain black hole physics, time dilation, and higher dimensional concepts in clear, compelling terms enabled the screenplay to educate audiences while maintaining dramatic momentum. The collaboration resulted in Thorne's book, The Science of Interstellar, which provides detailed explanations of every major scientific concept in the movie. This companion volume demonstrates the depth of scientific thinking that went into every story element, from the dust storms affecting Earth's agriculture to the physics of five-dimensional space. But perhaps Thorne's most important contribution was demonstrating that scientific accuracy could enhance rather than constrain creative storytelling. The physicist's constraints forced the filmmakers to find more innovative and interesting solutions than conventional science fiction shortcuts, resulting in scenarios that felt both fantastic and plausible. The relationship between Thorne and Christopher Nolan evolved into a genuine creative partnership where scientific insights informed artistic choices and artistic needs drove deeper exploration of physics concepts. This collaboration model challenged traditional assumptions about the relationship between science and entertainment. Thorne's presence on set during filming ensured real-time scientific consultation when questions arose about physical plausibility or technical accuracy. His willingness to engage with production challenges and find scientifically sound solutions to dramatic problems proved essential for maintaining accuracy throughout the complex filming process. The physicist's involvement in post-production extended to reviewing visual effects sequences frame by frame to ensure that phenomena like gravitational lensing, time dilation effects, and spacecraft behavior remained consistent with physical reality. This detailed attention to accuracy influenced every visual element in the finished film. Thorne's scientific foundation for Interstellar has had lasting impact beyond the movie itself, influencing how other filmmakers approach science fiction and demonstrating that audiences appreciate and respond to scientific authenticity when it's presented through compelling storytelling. The success of this collaboration has inspired other projects to involve working scientists more deeply in creative processes. The educational impact of Thorne's involvement extends through university physics courses that use interstellar scenes to explain complex concepts, NASA presentations that incorporate movie visuals to illustrate real physics, and public science communication efforts that build on the movie's popularity to engage broader audiences with actual scientific research. Recent gravitational wave detections by LIGO, the project Thorne helped create, have validated many of the concepts featured in Interstellar, demonstrating that the movie's scientific foundation was built on research that would later achieve Nobel Prize recognition. This connection between fictional narrative and actual scientific discovery illustrates the power of rigorous scientific consultation. The scientific foundation established by Kip Thorne's involvement transformed Interstellar from entertainment into education, from science fiction into science communication, and from Hollywood fantasy into a genuine contribution to public understanding of some of the most profound and beautiful concepts in modern physics. This foundation enables everything else about Interstellar's unprecedented accuracy, from black hole visualization to time dilation effects to realistic space travel, proving that starting with real science creates possibilities for storytelling that exceed what pure imagination alone could achieve. Understanding Thorne's foundational role reveals why Interstellar succeeded where other space movies fail. It built impossible scenarios on possible physics, creating fantasy that feels achievable through scientific understanding rather than magical thinking. Chapter 2: Black Hole Reality, the Creation of Gargantua. The massive black hole at the center of Interstellar represents perhaps the most scientifically accurate visualization of a black hole ever produced, resulting from an unprecedented collaboration between theoretical physicists and visual effects artists that actually advanced our scientific understanding of how these extreme objects would appear to human observers. This wasn't just Hollywood special effects. It was computational astrophysics that produced images so realistic they led to peer-reviewed scientific publications. The challenge of visualizing Gargantua began with Kip Thorne's insistence that the black hole behave according to Einstein's general relativity rather than science fiction conventions. This meant solving the full Einstein field equations to determine exactly how light rays would be bent, stretched, and distorted by the extreme gravitational fields near a rotating supermassive black hole with a mass 100 million times greater than our Sun. Visual effects supervisor Paul Franklin and his team at Double Negative worked directly with Thorne to develop new computational techniques for ray tracing light through the curved space-time around a curved black hole. The mathematical description of a rotating black hole developed by Roy Kerr in 1963. This required writing code that could simulate millions of light paths to create accurate images of how Gargantua would appear from different viewing angles. The resulting visualization revealed phenomena that surprised even the physicists involved in the project. The gravitational lensing effects around Gargantua created multiple images of the accretion disk, the superhot matter spiraling into the black hole that appeared above, below, and around the black hole's silhouette in ways that hadn't been clearly visualized before this computational breakthrough. Dr. James Bardine's early work on black hole imaging provided the theoretical foundation, but the Interstellar team extended these calculations to create the first accurate moving images of how accretion disk dynamics would appear to observers at various distances from a rotating black hole. The complex interplay of gravitational lensing, Doppler shifting, and relativistic beaming created a visual symphony of physics. The accretion disk itself required careful modeling of plasma physics, magnetic field dynamics, and relativistic fluid flow to accurately represent how matter behaves in the extreme environment near a black hole. The team consulted magnetohydrodynamic simulations to ensure that the disk structure, temperature distribution, and emission patterns reflected current understanding of black hole accretion. Physics, one of the most remarkable discoveries during visualization development, was the appearance of the disk's secondary image, light from the backside of the accretion disk that gets gravitationally lensed over the top of the black hole to become visible to observers on the front side. This effect creates the distinctive eyebrow appearance above Gargantua that surprised audiences and physicists alike. The color and brightness variations across Gargantua's accretion disk reflect real physics of relativistic Doppler shifting, where material moving toward the observer appears brighter and bluer, while material moving away appears dimmer and redder. These effects create the asymmetric brightness pattern that gives rotating black holes their characteristic appearance. Gravitational redshift effects near Gargantua's event horizon cause light from the innermost regions of the accretion disk to appear redder and dimmer than it would in flat spacetime. The team carefully calculated these effects to ensure that the color, gradients, and brightness distributions match theoretical predictions for light escaping from different distances from the black hole. The black hole's rotation, characterized by what physicists call the spin parameter, affects both the size of the event horizon and the behavior of matter in the accretion disk. For Interstellar's Gargantua, the team chose parameters that would create dramatic visual effects while remaining within the bounds of what's physically possible for real black holes. Frame-dragging effects, where the black hole's rotation literally drags spacetime around with it, influence how matter orbits in the accretion disk and affect the propagation of light near the black hole. These subtle but important effects required sophisticated general relativity calculations to model accurately in the visual representation. The absence of a visible jet in Gargantua's visualization reflects a specific choice about the black hole's magnetic field configuration and accretion rate. Many real black holes produce powerful relativistic jets perpendicular to their accretion disks, but the team chose parameters that would minimize jet activity to focus attention on the accretion disk and gravitational lensing effects. Tidal effects near Gargantua become important for spacecraft approaching the black hole, though these effects are minimized by the black hole's enormous mass. For supermassive black holes like Gargantua, the tidal forces at the event horizon are actually quite gentle, allowing objects to cross the horizon without being immediately destroyed. A crucial plot point for the movie's climax, the time dilation effects near Gargantua result from the black hole's intense gravitational field, which slows the passage of time according to general relativity. The team calculated exactly how much time dilation would occur at different distances from the black hole, leading to the 1 hour equals 7 years scenario on Miller's planet. Gravitational wave production from objects orbiting near Gargantua represents another aspect of black hole physics that the team considered, though these effects remain largely invisible in the movie's timeframe. The LIGO gravitational wave discoveries that came after Interstellar's release validated many of the black hole concepts featured in the film. The visual rendering of Gargantua required developing new computer graphics techniques for handling the complex ray tracing calculations needed to simulate gravitational lensing effects. The team created custom software that could track millions of light rays through curved spacetime to generate physically accurate images. Temperature gradients in Gargantua's accretion disk follow the theoretical predictions for black hole accretion theory, with inner regions reaching temperatures of millions of degrees, while outer regions remain relatively cool. These temperature differences create the color variations visible in the final visualization. Boundary between the accretion disk and empty space around Gargantua reflects the physics of the innermost stable circular orbit, ISCO, beyond which matter cannot maintain stable orbits and must either escape to infinity or fall into the black hole. This boundary creates the sharp inner edge of the accretion disk visible in the movie. Magnetic field effects in Gargantua's accretion disk influence plasma dynamics and energy transport. Though these largely invisible effects were incorporated into the modeling rather than being explicitly visualized, the team consulted magnetohydrodynamics experts to ensure that the disk structure reflected realistic magnetic field configurations. The scientific accuracy of Gargantua's visualization extended beyond visual appearance to include proper treatment of relativistic effects on spacecraft navigation, communication delays caused by gravitational time dilation, and the orbital mechanics of objects moving through the complex spacetime geometry near a rotating black hole. Post-release analysis of Gargantua's visualization by the astrophysics community has validated the accuracy of the rendering techniques and led to new insights about black hole appearance. Several scientific papers have cited the interstellar visualizations as contributing to our understanding of how real black holes would appear to human observers. The computational breakthrough achieved for Interstellar has influenced subsequent black hole visualizations in both scientific research and popular media. The Event Horizon Telescope team that produced the first real black hole image in 2019 used similar ray tracing techniques to predict how their observations should appear. Educational impact of Gargantua's accurate visualization extends through university astrophysics courses that use movie clips to explain black hole physics, planetarium shows that incorporate interstellar imagery, and public science communication efforts that build on the movie's visual accuracy to teach about extreme gravity. The black hole reality created for Interstellar thus represents far more than movie magic. It's a genuine scientific achievement that advanced our understanding of black hole physics while proving that rigorous accuracy can enhance rather than constrain visual storytelling. Gargantua remains the most scientifically accurate black hole ever depicted in popular media. This achievement demonstrates how collaboration between scientists and artists can produce results that exceed what either community could accomplish alone, creating visualizations that serve both entertainment and education, while advancing actual scientific understanding of the universe's most extreme objects. Chapter 3. Time Dilation Truth. Interstellar's treatment of time dilation represents the most accurate portrayal of Einstein's general relativity ever depicted in popular media, showing how extreme gravitational fields slow the passage of time in ways that create genuine emotional drama from pure physics. The movie's famous 1 hour equals 7 years scenario on Miller's planet emerges from rigorous calculations of how time flows differently near massive objects, transforming abstract relativity theory into visceral human experience. The physics of gravitational time dilation was first predicted by Einstein's general relativity, which shows that time passes more slowly in stronger gravitational fields. This effect occurs because gravity and acceleration are fundamentally equivalent, and accelerated motion affects the rate at which time flows according to the principles of special and general relativity combined. Dr. Kip Thorne worked extensively with the filmmakers to calculate exactly how much time dilation would occur on a planet orbiting close to a black hole with Gargantua's mass and rotation parameters. The resulting mathematics showed that the extreme scenario depicted in the movie, while dramatic, falls within the bounds of what's physically possible near supermassive black holes. Miller's planet orbits Gargantua at a distance where the gravitational time dilation factor reaches approximately 61,000, meaning that 1 hour on the planet's surface corresponds to 7 years for observers far from the black hole's gravitational influence. This extreme ratio emerges from the planet's proximity to the black hole's event horizon, where space-time curvature approaches its maximum possible values. The movie correctly depicts how time dilation affects different characters based on their location relative to Gargantua's gravitational field. Cooper and Brand experience extreme time dilation on Miller's planet, while Romilly, orbiting farther from the black hole aboard the Endurance, ages at a rate intermediate between the planet's surface and Earth normal time. Gravitational redshift effects accompany time dilation, causing light from regions of stronger gravity to appear redder when observed from regions of weaker gravity. The movie incorporates these effects subtly, showing how communication signals between different locations near Gargantua would be affected by gravitational frequency shifts. The emotional impact of time dilation in Interstellar emerges from its effects on human relationships and life cycles. Cooper's return from Miller's planet to find that Romilly has aged 23 years while Cooper experienced only hours demonstrates how relativity theory creates dramatic stakes about mortality, aging, and the passage of human lives. The GPS satellite system provides a real-world example of time dilation effects that audiences can relate to. GPS satellites experience time dilation due to their orbital motion and reduced gravitational field compared to Earth's surface, requiring corrections of approximately 38 microseconds per day to maintain accuracy. Interstellar scales these familiar effects to extreme proportions. Tidal effects near Gargantua create additional complications for time dilation calculations because different parts of Miller's planet experience slightly different gravitational fields. The movie simplifies these effects for dramatic clarity while maintaining overall accuracy about the dominant time dilation phenomenon. The wave-covered surface of Miller's planet reflects realistic consequences of tidal forces from Gargantua's gravity, which would create massive ocean waves by stretching the planet's oceans toward and away from the black hole. These waves represent permanent standing waves locked in position by tidal forces rather than moving waves like those on Earth. Time dilation effects on biological processes mean that Cooper and Brand's metabolisms, aging, and neural activity all slow down proportionally when they're on Miller's planet. This biological time dilation ensures that they experience normal subjective time despite the extreme gravitational environment they're experiencing. The synchronization of clocks between different locations near Gargantua requires careful consideration of relativistic effects. The movie correctly shows that timekeeping becomes relative rather than absolute when characters operate in dramatically different gravitational environments, making coordination challenging. Communication delays between Miller's planet and the Endurance involve both signal travel time and time dilation effects. Messages sent from the planet's surface would appear to be transmitted at extremely slow rates when received by observers in weaker gravitational fields, creating additional challenges for coordination. The energy requirements for escaping from Miller's planet reflect the extreme gravitational potential differences involved in climbing out of the black hole's gravitational well. The movie correctly emphasizes the fuel and energy costs associated with traveling between regions of different gravitational potential. Historical precedents for time dilation observations include atomic clock experiments on airplanes, satellite timing corrections, and particle accelerator observations of muon decay rates. These real-world measurements confirm Einstein's predictions and provide experimental validation for the extreme extrapolations depicted in Interstellar. The twin paradox from special relativity provides a useful analogy for understanding Interstellar's time dilation effects. Though the movie deals with gravitational rather than velocity-based time dilation, both effects demonstrate how time is relative rather than absolute, challenging common sense assumptions about temporal flow. Schwarzschild Radius calculations for Gargantua determine the distance from the black hole. Where time dilation becomes infinite, the event horizon itself. Miller's planet orbits just outside this critical radius, placing it in the region of maximum possible time dilation while still allowing escape. Frame dragging effects from Gargantua's rotation influence both time dilation and the orbital mechanics of Miller's planet. The black hole's spin drags space-time around with it, creating additional relativistic effects that the movie incorporates into its depiction of the planet's environment proper. Time versus coordinate time distinctions become crucial for understanding Interstellar's time dilation scenarios. Proper time is what characters experience locally, while coordinate time represents measurements made by distant observers, explaining how the same events can have dramatically different durations. The equivalence principle, which states that gravity and acceleration are indistinguishable, helps explain why extreme gravitational fields create time dilation effects similar to those experienced during acceleration. This principle underlies all of general relativity and provides the foundation for Interstellar's time manipulation. Horizon crossing scenarios in general relativity show that objects falling into black holes experience finite proper time to reach the event horizon, even though distant observers see them frozen at the horizon due to infinite gravitational redshift. Interstellar uses these effects in Cooper's final journey into Gargantua, as into conformental confirmations of time dilation include measurements of atomic clocks at different altitudes, observations of GPS satellite timing corrections, and high-energy physics experiments that confirm relativistic time effects. These real-world validations support the extreme extrapolation shown in the movie. The universality of time dilation effects means that all physical processes, biological, chemical, nuclear, and quantum, experience the same proportional slowing in gravitational fields. This ensures that characters experiencing extreme time dilation don't notice anything unusual about their local environment. Causality. Preservation in relativity theory prevents time dilation from creating paradoxes or allowing communication with the past. The movie respects these constraints by showing how time dilation affects different observers without creating causal loops or logical contradictions. Future experimental tests of extreme time dilation might involve observations of matter falling into black holes, precision timing experiments in strong gravitational fields, and gravitational wave observations that test general relativity under extreme conditions. These experiments could validate the scenarios depicted in Interstellar. Educational applications of Interstellar's time dilation scenes have transformed how physics instructors explain relativity concepts to students. The movie provides visceral, emotional examples of abstract physics concepts that help students understand why relativity matters and how it affects real phenomena. The time dilation truth revealed in Interstellar demonstrates that Einstein's century-old theory continues to yield insights into the nature of time, space, and gravity that can create compelling drama while remaining rigorously accurate to known physics. The movie proves that scientific truth can be more amazing than fiction. This accurate treatment of time dilation effects shows how understanding real physics can enhance storytelling by creating genuine stakes based on the fundamental nature of reality rather than arbitrary dramatic devices. The emotional power of Cooper's aging while his daughter grows old emerges directly from Einstein's equations. Chapter 4. Space Travel Physics. Interstellar's depiction of space travel represents one of the most scientifically rigorous treatments of orbital mechanics, propulsion physics, and spacecraft engineering ever presented in popular media. Unlike most space movies that ignore the harsh realities of Newtonian physics, Interstellar shows space travel as the difficult, dangerous, and energy-intensive endeavor it actually is, using real physics constraints to create dramatic tension and authentic technical challenges. The Endurance spacecraft design reflects serious consideration of the engineering requirements for long-duration interstellar missions. Its modular construction, rotating sections for artificial gravity, and specialized landing craft represent realistic approaches to spacecraft architecture based on current understanding of space engineering and human factors in long-duration flight. Artificial gravity generation through rotation demonstrates accurate physics of centrifugal force and angular momentum. The Endurance's rotating sections create artificial gravity through centripetal acceleration, showing how future spacecraft might provide Earth-like environments for crew health and operational efficiency during multi-year missions. The docking sequence between Cooper's Ranger and the tumbling Endurance represents one of the most accurate portrayals of orbital mechanics and spacecraft maneuvering ever filmed. The physics of angular momentum conservation, relative motion, and propulsive maneuvering all align with real spaceflight dynamics, creating tension through authentic technical challenges. Dr. Kip Thorne worked with aerospace consultants to ensure that spacecraft trajectories, fuel requirements, and orbital mechanics reflected real physics rather than Hollywood convenience. Every spacecraft movement in the movie can be justified through Newtonian mechanics and realistic propulsion capabilities, gravitational assist maneuvers using planetary flybys demonstrate sophisticated understanding of orbital mechanics and trajectory planning. The spacecraft's path through the solar system incorporates realistic gravitational slingshot effects that real space missions use to achieve high velocities while conserving fuel. The absence of sound in space represents a commitment to physics accuracy that distinguishes Interstellar from most space movies. Sound waves require matter to propagate, and the vacuum of space cannot transmit acoustic vibrations, making space inherently silent despite the drama and tension of spacecraft operations. Propulsion system limitations create realistic constraints on mission planning and emergency responses. The movie shows how fuel requirements, thrust-to-weight ratios, and delta-V budgets affect what spacecraft can accomplish, forcing characters to make difficult choices based on engineering realities rather than dramatic convenience. Launch sequences from Earth accurately depict the enormous energy requirements for escaping planetary gravity wells. The massive Saturn V-class rockets shown in the movie reflect realistic staging, fuel consumption, and acceleration profiles needed to achieve orbital velocity and begin interstellar missions. Atmospheric entry and landing procedures on alien worlds incorporate real atmospheric physics, heat management, and landing dynamics. The Ranger craft's entry into thick atmospheres shows realistic heating effects, atmospheric braking, and the challenges of landing on worlds with different atmospheric compositions and gravitational fields. Zero gravity effects aboard spacecraft demonstrate accurate understanding of how microgravity affects human physiology, fluid dynamics, and equipment operation. Characters move and behave in ways consistent with actual spaceflight experience, avoiding the common movie mistake of treating space travel like atmospheric flight. Spacecraft structural engineering considerations include radiation shielding, micrometeorite protection, and thermal management systems necessary for long-duration interstellar travel. The Endurance's design reflects realistic approaches to protecting crew and equipment from space environment, Hazards. Navigation challenges in Interstellar. Space requires sophisticated understanding of celestial mechanics, stellar positions, and navigation techniques. The movie shows how spacecraft must maintain orientation and determine position using astronomical reference points when traveling between star systems. Life support systems aboard the Endurance incorporate realistic constraints on air recycling, water management, food production, and waste processing needed to sustain human crews during multi-year missions. These systems represent extensions of current International Space Station technologies. Cryogenic hibernation systems, while speculative, reflect serious scientific research into suspended animation for long-duration space missions. The movie's treatment of hibernation technology remains grounded in biological and medical research while acknowledging current technological limitations. Communication delays over interstellar distances accurately reflect the finite speed of light and the challenges of maintaining contact across cosmic distances. The movie shows how signal transmission times of years create coordination challenges and emotional isolation for interstellar travelers. Fuel consumption calculations for interstellar missions involve enormous energy requirements that constrain mission architecture and spacecraft design. The movie demonstrates understanding of how fuel mass requirements scale with mission duration and destination distances. Spacecraft maintenance and repair capabilities become critical for long-duration missions where Earth-based support is impossible. The Endurance carries manufacturing equipment and spare parts necessary for maintaining complex systems during multi-year interstellar journeys. Orbital mechanics around alien worlds require understanding how different planetary masses, atmospheres, and rotation rates affect spacecraft operations. The movie shows realistic orbital insertion procedures and the challenges of operating in unfamiliar gravitational environments. Emergency procedures and abort scenarios reflect realistic mission planning for catastrophic failures. The movie demonstrates how spacecraft crews must prepare for system failures, medical emergencies, and mission-threatening scenarios when rescue from Earth is impossible. Human factors engineering considerations include crew psychology, social dynamics, and the challenges of maintaining human performance during long isolation missions. The movie explores how interpersonal relationships and psychological stress affect mission success in realistic ways. Radiation exposure in deep space represents a serious health hazard for interstellar travelers that the movie acknowledges through shielding requirements and mission planning considerations. Solar and cosmic radiation create ongoing health risks that constrain mission duration and crew safety. Spacecraft systems redundancy and backup capabilities reflect aerospace engineering principles for mission-critical systems. The Endurance incorporates multiple redundant systems and backup procedures necessary for maintaining spacecraft function when repair resources are limited. Aerodynamic considerations for atmospheric flight within planetary atmospheres require different design approaches than space-only vehicles. The Ranger craft demonstrate realistic compromises between space efficiency and atmospheric flight capability. Docking mechanisms and inter-vehicle transfer procedures follow realistic engineering approaches for connecting spacecraft modules and transferring crew between vehicles. These operations require precision maneuvering and mechanical interfaces that function reliably in space environments. Thermal management systems for spacecraft operating at different distances from stars require sophisticated heat rejection and temperature control capabilities. The movie shows how spacecraft must adapt to varying thermal environments throughout interstellar missions. emergency escape and survival equipment aboard. Spacecraft reflect realistic preparations for catastrophic failures and abandonment scenarios. Life pods and emergency supplies represent essential safety systems for missions where rescue operations are impossible. The physics of space travel, depicted in Interstellar, demonstrates that realistic constraints enhance rather than limit dramatic storytelling by creating authentic technical challenges that characters must overcome through skill, knowledge, and determination rather than technological magic. Future space missions will likely incorporate many of the engineering solutions and operational procedures depicted in Interstellar, making the movie's realistic approach valuable for inspiring and educating future space explorers about the genuine challenges and excitement of Interstellar travel. The commitment to space travel. Physics accuracy in Interstellar proves that audiences appreciate and respond to technical authenticity when it serves compelling human stories, challenging assumptions that scientific realism must be sacrificed for mainstream entertainment appeal. Understanding the real physics of space travel as depicted in Interstellar reveals why actual space exploration requires such extraordinary technological achievements and human dedication, making real astronauts and engineers even more heroic than fictional space travelers. Chapter 5. Planetary Science. Interstellar's alien worlds represent some of the most scientifically accurate planetary environments ever depicted in science fiction. Based on rigorous exoplanet research, atmospheric physics, and geological processes that could realistically exist on worlds orbiting other stars. Each planet visited in the movie reflects careful consideration of how different atmospheric compositions, gravitational fields, and stellar environments would create unique but plausible alien landscapes. Miller's planet, orbiting close to the black hole Gargantua, demonstrates realistic consequences of extreme tidal forces on planetary geology and hydrology. The planet's ocean-covered surface and massive standing waves represent accurate physics of how a world locked in tidal synchronization with a massive gravitational source would behave, creating permanent wave structures that remain fixed in position. The shallow ocean covering Miller's planet reflects realistic atmospheric and hydrological cycles on a tidally locked world. Water distribution, atmospheric circulation, and cloud formation patterns all demonstrate understanding of how planetary climate systems would adapt to the extreme gravitational environment near a supermassive black hole. Dr. Mann's ice planet showcases accurate physics of atmospheric composition, cloud formation, and surface conditions on a world with different atmospheric chemistry than Earth. The frozen ammonia, clouds, and surface ice structures represent plausible atmospheric compositions for planets in different stellar environments or evolutionary stages. Atmospheric physics on Mann's planet includes realistic treatment of how different gas compositions affect optical properties, weather patterns, and surface conditions. The planet's appearance and behavior reflect scientific understanding of how varying atmospheric constituents would create different planetary environments. Surface gravity effects on each alien world accurately reflect how planetary mass affects human movement, equipment operation, and vehicle performance. The movie shows subtle but realistic differences in how characters move and objects behave under different gravitational conditions. Edmund's planet represents realistic desert world conditions based on current understanding of planetary climate, evolution, and atmospheric loss processes. The planet's arid surface, dust storms, and rocky terrain reflect plausible outcomes of planetary atmospheric evolution in different stellar environments. Atmospheric composition. Analysis throughout the movie demonstrates realistic approaches to planetary exploration and habitability assessment. The use of spectrographic analysis, atmospheric sampling, and environmental monitoring reflects actual techniques used by planetary scientists and astrobiologists. Tidal locking effects on planetary rotation and climate create realistic asymmetric heating patterns. Atmospheric circulation and surface temperature distributions. The movie incorporates understanding of how synchronous rotation affects planetary climate systems and surface conditions. Geological processes on alien worlds reflect realistic rock formation, erosion patterns, and surface evolution under different gravitational and atmospheric conditions. The varied terrain on each planet demonstrates understanding of how different physical environments would shape planetary geology. Water presence and distribution on alien worlds follows realistic constraints based on planetary temperature, atmospheric pressure, and chemical composition. The movie shows how water exists in different phases and distributions, depending on local planetary conditions. Atmospheric pressure effects on human physiology and equipment operation demonstrate accurate understanding of how different atmospheric conditions would affect spacesuit requirements, breathing apparatus, and human survival capabilities on alien worlds. Solar radiation and stellar environment effects on planetary atmospheres reflect realistic understanding of how different stellar types and distances would affect planetary heating, atmospheric chemistry, and surface conditions. Each planet's environment reflects its position relative to available energy sources. Dust storm physics on Edmund's planet demonstrates accurate understanding of atmospheric dynamics, particle transport, and visibility conditions during severe weather events. The storm's behavior reflects realistic atmospheric physics scaled to different planetary conditions. Chemical composition variations in planetary atmospheres and surfaces reflect realistic understanding of how different formation processes and evolutionary histories would create diverse planetary environments with varying chemical signatures and resource availability. Magnetic field effects on planetary atmospheres and radiation environments demonstrate understanding of how planetary magnetic fields protect surface environments from stellar radiation and affect atmospheric retention over geological timescales. Seasonal variations on alien worlds reflect realistic orbital mechanics and atmospheric response to changing solar heating patterns. The movie incorporates understanding of how orbital characteristics would affect planetary climate cycles and environmental conditions. Atmospheric escape processes that affect long-term planetary evolution demonstrate understanding of how stellar radiation, planetary mass, and magnetic field strength affect atmospheric retention and the evolution of planetary environments over cosmic timescales. Surface temperature distributions on each planet reflect realistic energy balance calculations considering atmospheric composition, greenhouse effects, and heat transport mechanisms. The movie shows plausible temperature ranges based on distance from energy sources and atmospheric properties. Exoplanet research discoveries inform the realistic planetary environments depicted in Interstellar. The movie incorporates knowledge gained from Kepler telescope observations, atmospheric spectroscopy, and theoretical modeling of planetary formation and evolution processes. Habitability factors considered for each world include realistic assessment of temperature ranges, atmospheric composition, water availability, and radiation environments. The movie demonstrates scientific approaches to evaluating planetary suitability for human colonization, atmospheric optical effects on each planet, including sky color, visibility conditions, and light scattering patterns reflect accurate physics of how different atmospheric compositions would affect the appearance of planetary environments from human observers' perspectives. Planetary formation processes implied by each world's characteristics demonstrate understanding of how different formation scenarios, solar environments, and evolutionary histories would create the diverse planetary environments encountered during the mission. Surface material properties on alien worlds, including soil composition, rock types, and chemical weathering patterns, reflect realistic understanding of how different atmospheric and geological processes would create distinctive surface characteristics on different planets. Biological potential assessment for each world incorporates realistic astrobiology principles for evaluating planetary environments' capacity to support life, either indigenous organisms or human colonization efforts. Atmospheric dynamics and weather patterns on each planet demonstrate understanding of fluid mechanics, thermodynamics, and atmospheric circulation under different gravitational and heating conditions. Weather systems reflect realistic physics scaled to different planetary parameters. Resource availability assessment on alien worlds includes realistic evaluation of water resources, atmospheric gases, mineral deposits, and energy sources that would be necessary for establishing human colonies or supporting long-term exploration missions. Planetary protection considerations throughout the movie reflect current protocols for preventing contamination of alien environments and protecting Earth from potential biological hazards, demonstrating awareness of responsible planetary exploration practices. Environmental hazards on each world, including radiation exposure, atmospheric toxicity, and physical dangers, reflect realistic assessment of the challenges human explorers would face on different types of alien worlds based on current understanding of planetary environments, terraforming potential and challenges. For each world, demonstrate understanding of planetary engineering concepts and the enormous technological requirements that would be necessary to modify alien environments for human habitability. Comparative planetology principles underlying the diverse worlds in Interstellar reflect scientific approaches to understanding how different physical conditions create the variety of planetary environments observed in our solar system and beyond. The planetary science accuracy in Interstellar demonstrates that realistic alien worlds can be more fascinating and dramatically compelling than purely imaginary environments, showing how scientific understanding enhances rather than constrains creative possibilities. For depicting alien landscapes, this commitment to planetary realism provides educational value by demonstrating the diversity and complexity of planetary environments while showing how scientific principles govern the formation and evolution of worlds throughout the universe. The realistic planetary environments in Interstellar inspire scientific curiosity about exoplanet research and planetary exploration, while providing accurate representations of the challenges and wonders that future human explorers might encounter on other worlds. Chapter 6: Quantum Mysteries. Interstellar's exploration of higher dimensional physics and quantum mechanics ventures into the most speculative yet scientifically grounded territory in the movie, presenting concepts from cutting-edge theoretical physics that remain at the frontiers of human understanding. The Tesseract sequence and five-dimensional beings, while necessarily speculative, emerge from serious theoretical frameworks developed by string theorists, cosmologists, and quantum gravity researchers. The Tesseract construction, where Cooper experiences time as a Navigable spatial dimension represents a visualization of theoretical concepts from general relativity and cosmology. About the nature of space-time dimensionality, Dr. Kip Thorne worked with theoretical physicists to ensure that this sequence, while fantastical, remained consistent with serious speculation about higher dimensional physics, five-dimensional space-time theories, particularly those emerging from string theory and Kaluza-Klein cosmology, provide the theoretical foundation for the movie's depiction of beings capable of manipulating four-dimensional space-time from a higher dimensional perspective. These theories suggest that additional spatial dimensions might exist beyond our direct perception. The visualization of time as a spatial dimension in the Tesseract reflects theoretical work in general relativity, where time and space are unified into four-dimensional space-time. The movie extends this concept by suggesting how additional spatial dimensions might enable navigation through time in ways impossible within four-dimensional space-time. Gravitational manipulation across time, as demonstrated by Cooper's ability to affect past events through gravitational anomalies, represents speculative but theoretically consistent extensions of general relativity. Einstein's equations permit closed time-like curves under certain exotic matter conditions. Though such configurations remain purely theoretical, quantum mechanics and consciousness connections explored in Interstellar reflect serious theoretical work on the measurement problem and the role of observation in quantum mechanical phenomena. The movie suggests that consciousness might play fundamental roles in quantum mechanical processes, though these ideas remain controversial among physicists. The grandfather paradox resolution implied by Interstellar's time manipulation scenarios requires careful consideration of causality and information flow in theories that permit closed time-like curves. The movie suggests self-consistent causal loops where effects create their own causes without logical contradictions. String theory's extra dimensions provide theoretical justification for the higher dimensional beings depicted in Interstellar. String theory requires 6 or 7 additional spatial dimensions beyond our familiar 3. Suggesting that sufficiently advanced beings might access these dimensions directly. Moke space and brain world cosmology, developed by theorists like Lisa Randall and Raymond Sundrum, propose that our four-dimensional space-time might exist as a brain embedded in higher dimensional bulk space. This framework could allow higher dimensional beings to interact with our space-time from external perspectives. The bootstrap paradox, implicit in Interstellar's causal structure, where human survival depends on future humans helping their past selves, reflects complex theoretical work on self-consistent causal loops and the information paradox in quantum gravity theories. Holographic principle applications to the Tesseract suggest that higher dimensional information might be encoded on lower dimensional boundaries, similar to how three-dimensional images can be reconstructed from two-dimensional holographic plates. This principle might enable higher dimensional beings to access complete information about lower dimensional SPAC, ETIME. Quantum entanglement and non-local correlations provide theoretical foundations for the instantaneous communication across space and time depicted in Interstellar's Tesseract sequence. While speculative, these connections reflect serious theoretical work on non-locality and quantum mechanics. Information theory and black hole physics inform the movie's treatment of how information might be preserved and transmitted across space-time boundaries. The black hole information paradox and recent theoretical developments suggest complex relationships between information, gravity, and space-time structure. Emergence theory in physics suggests that macroscopic phenomena like space-time geometry, might emerge from more fundamental microscopic processes, possibly involving quantum information processing. This theoretical framework could provide foundations for consciousness space-time interactions depicted in the Thorne movie. Anthropic reasoning in cosmology suggests that physical constants in space-time properties might be fine-tuned for consciousness emergence, creating relationships between cosmic evolution and observer existence. Interstellar explores how these relationships might extend to consciousness affecting space-time structure. Quantum field theory in curved space-time predicts particle creation and vacuum fluctuations near black holes and other extreme gravitational environments. The movie's tesseract environment might represent regions where quantum gravitational effects become macroscopically apparent. The measurement problem in quantum mechanics involves unresolved questions about how classical reality emerges from quantum superposition states. Some interpretations suggest consciousness plays fundamental roles in this process, providing theoretical foundations for the movies. Consciousness spacetime connections. Causal loop quantum gravity theories explore how quantum mechanical processes might permit closed causal loops without creating logical paradoxes. These theoretical frameworks could justify the self-consistent time manipulation depicted in Interstellar's climax. Many worlds' interpretation of quantum mechanics suggests that all possible quantum outcomes occur in parallel universes, creating frameworks where time manipulation might involve accessing alternate quantum histories rather than changing single timeline events. Consciousness theories in quantum mechanics, from Henry Stapp's consciousness-based interpretations to Roger Penrose's orchestrated objective reduction, explore relationships between awareness and quantum mechanical processes that could provide foundations for consciousness affecting spacetime. Dark energy and dark matter physics might involve higher dimensional effects or exotic spacetime properties that could provide mechanisms for the advanced physics depicted in Interstellar's tesseract sequence. These mysterious cosmic components might operate through physics beyond current understanding. Information geometry and quantum information theory explore how information might have geometric properties and how geometric relationships might encode quantum mechanical phenomena. These theoretical frameworks suggest deep connections between information, consciousness, and spacetime structure. Emergent spacetime theories in quantum gravity suggest that spacetime geometry might emerge from more fundamental quantum information processing, creating frameworks where consciousness and spacetime could share common informational foundations. The holographic entropy bound limits the amount of information that can be contained within any region of spacetime, creating constraints on information processing capabilities that might affect consciousness spacetime interactions of the type depicted in Interstellar. Quantum error correction in spacetime theories explores how information might be preserved and processed in quantum gravitational systems, providing mechanisms for the information transmission and manipulation depicted in the movie's higher dimensional sequences. Future theoretical developments in quantum gravity, string theory, and consciousness studies might validate or refute the speculative physics depicted in Interstellar's quantum mysteries. The movie's grounding in current theoretical work makes these scenarios scientifically respectable, if highly speculative. Experimental tests of higher dimensional physics through particle accelerator experiments, gravitational wave observations, and precision tests of gravity might reveal whether the extra dimensions and exotic spacetime properties depicted in Interstellar actually exist in nature. The quantum mysteries explored in Interstellar demonstrate how serious theoretical physics can inspire compelling, dramatic scenarios while remaining grounded in mathematical frameworks developed by working physicists. The movie shows that speculative science can enhance storytelling when based on rigorous theoretical foundations. Educational value of Interstellar's quantum sequences includes introducing audiences to cutting-edge theoretical concepts that represent active areas of research in fundamental physics, inspiring interest in advanced topics that might seem inaccessible without dramatic visualization. Balance between speculation and scientific grounding in Interstellar's quantum mysteries shows how science fiction can explore theoretical frontiers while maintaining respect for scientific methodology and logical consistency, creating scenarios that feel both impossible and plausible. Understanding the theoretical foundations underlying Interstellar's quantum mysteries reveals how the movie transforms abstract mathematical concepts into emotionally compelling dramatic scenarios that explore the deepest questions about reality, consciousness, and humanity's place in cosmic evolution. Chapter 7. Agricultural Crisis. Interstellar's depiction of Earth's agricultural collapse represents one of the most scientifically accurate portrayals of ecological crisis ever presented in cinema. Based on real agricultural science, climate research, and environmental biology that shows how food production systems could realistically fail under environmental pressures. The movie's environmental themes reflect current understanding of agricultural sustainability, soil health, and the complex ecological relationships that support global food security. The blight affecting Earth's crops in Interstellar represents a realistic biological threat based on actual plant pathogens that have caused historical agricultural disasters. Dr. Kip Thorne consulted with agricultural scientists and plant pathologists to ensure that the fictional blight exhibited realistic characteristics consistent with fungal or bacterial pathogens that attack crop plants. Monoculture agriculture. Vulnerability depicted in the movie reflects real concerns about modern farming practices that rely on genetically uniform crop varieties susceptible to rapid pathogen spread. The concentration of global food production in a few major crops creates systemic risks similar to those shown in Interstellar's agricultural collapse scenario. Dust Bowl conditions affecting the American Midwest in the movie draw direct parallels to the 1930s Dust Bowl, incorporating realistic understanding of soil erosion, wind patterns, and agricultural practices that can lead to massive soil loss and agricultural land degradation. Atmospheric oxygen depletion caused by the dying vegetation represents accurate understanding of photosynthesis and global oxygen cycles. Plants produce most of Earth's atmospheric oxygen, so widespread vegetation death could theoretically reduce atmospheric oxygen levels, though the time frames involved would likely be longer than depicted in the movie. Soil degradation processes shown in Interstellar reflect real mechanisms of agricultural land loss, including erosion, nutrient depletion, salinization, and contamination. These processes represent genuine threats to global food security that agricultural scientists actively study and attempt to mitigate through improved farming practices. Climate change effects on agriculture. While not explicitly featured as the primary cause in Interstellar, provide contextual background for understanding how environmental stresses could make crops more vulnerable to pathogens and reduce overall agricultural productivity across different regions. Nitrogen cycle disruption, implied by the widespread plant death, would affect soil fertility and ecosystem function in realistic ways. Nitrogen-fixing bacteria in plant roots contribute essential nutrients to soil systems, so their loss would create cascading effects on soil health and agricultural productivity. food chain collapse scenarios depicted in the movie reflect ecological understanding of how agricultural failures affect livestock production, wildlife populations, and human nutrition. The interconnected nature of food systems means that crop failures create multiple cascading effects throughout ecological and economic systems. Historical precedents for agricultural disasters include the Irish potato famine, wheat rust epidemics, and various crop failures that have caused famines and social disruption. Interstellar's scenario represents an extreme version of agricultural crises that have occurred repeatedly throughout human history. Plant pathogen evolution and adaptation represent ongoing threats to agricultural security as pathogens evolve resistance to treatments and adapt to new crop varieties. The arms race between crop breeders and pathogen evolution provides realistic foundations for the escalating agricultural crisis depicted in the movie. Pesticide resistance development in agricultural pests reflects real processes that could contribute to agricultural vulnerability. The overuse of chemical treatments can lead to resistant pathogen populations that become increasingly difficult to control through conventional agricultural methods. Genetic diversity loss in agricultural crops represents a genuine threat to food security, as traditional crop varieties are replaced by uniform commercial varieties. This genetic bottleneck creates vulnerability to new pathogens that can spread rapidly through genetically similar crop populations. Seed preservation efforts, like those implied by the agricultural scientists in Interstellar, reflect real seed bank programs that maintain genetic diversity and preserve crop varieties against future agricultural threats. These programs represent essential insurance against agricultural disasters. Soil microbiome health affects plant disease resistance and overall agricultural productivity through complex interactions between beneficial and pathogenic microorganisms. Disruption of soil microbial communities could contribute to the type of agricultural collapse depicted in the movie. Pollinator decline effects on agricultural production reflect current environmental concerns about bee colony collapse and other threats to pollinating insects. Many crop plants require animal pollination, so pollinator loss could contribute to reduced agricultural yields and food system vulnerability. Water resource depletion and contamination represent additional environmental stresses that can exacerbate agricultural crises. Drought conditions, groundwater depletion, and water pollution all affect agricultural productivity and could contribute to the type of environmental collapse shown in Interstellar. Industrial agriculture dependency on fossil fuels for fertilizers, pesticides, and machinery creates vulnerabilities to energy supply disruptions. The complex infrastructure supporting modern agriculture requires enormous energy inputs that could become limiting factors during environmental crises. Global trade disruption effects on food security reflect how modern agriculture depends on international supply chains for seeds, fertilizers, equipment, and food distribution. Local agricultural failures can have global impacts through interconnected economic and logistical systems. Alternative agriculture research and development, including vertical farming, hydroponics, and genetic engineering, represent potential solutions to agricultural crises. The movie's focus on space colonization reflects one extreme response to irreversible environmental collapse. Ecosystem service collapse beyond food production includes effects on water purification, soil formation, climate regulation, and biodiversity conservation. Agricultural landscapes provide multiple environmental benefits, whose loss would create cascading ecological and economic effects. Emergency food production strategies during agricultural crises might include rationing systems, alternative protein sources, and modified diets that the movie depicts through background details about dietary restrictions and food scarcity affecting daily life. Societal adaptation responses to agricultural collapse include population migration, social reorganization, and technological innovation. Interstellar shows realistic social responses, including educational system changes that prioritize practical skills over academic subjects perceived as less essential. Conservation agriculture practices that could help prevent agricultural disasters include crop rotation, cover cropping, integrated pest management, and soil health improvement. These practices represent real strategies for building agricultural resilience against environmental stresses. Plant breeding and biotechnology research offer potential solutions for developing crop varieties resistant to specific pathogens or environmental stresses. The ongoing development of disease-resistant crops represents a scientific response to agricultural vulnerability. International cooperation on agricultural security includes sharing genetic resources, coordinating research efforts, and developing global response strategies for agricultural emergencies. These collaborative efforts could help prevent or mitigate agricultural disasters like those depicted in Interstellar. The realistic agricultural crisis depicted in Interstellar serves multiple narrative functions while maintaining scientific accuracy about genuine environmental threats facing global food security. The movie demonstrates how environmental challenges create urgency for space exploration while grounding space travel in realistic terrestrial motivations. Educational value of Interstellar's environmental themes includes raising awareness about agricultural vulnerability, soil conservation, and the complex ecological relationships supporting human civilization. The movie helps audiences understand how environmental science connects to space exploration priorities. Research connections between the movie's environmental themes and actual agricultural science include ongoing studies of crop disease resistance, soil health, climate change impacts on agriculture, and sustainable farming practices that could prevent the type of agricultural collapse depicted in the film. The agricultural crisis in Interstellar thus represents scientifically grounded speculation about how environmental degradation could threaten human civilization while providing realistic motivation for interstellar exploration as humanity's ultimate survival strategy. The movie shows how environmental science and space science connect through shared concerns about human survival and planetary stewardship. This realistic treatment of agricultural vulnerability demonstrates that environmental challenges can create compelling dramatic stakes while educating audiences about genuine scientific concerns that require serious attention and innovative solutions to prevent real-world agricultural disasters. Chapter 8. Human Elements. Interstellar's greatest achievement lies in seamlessly weaving hard science with deeply human emotions, proving that scientific accuracy can enhance rather than diminish emotional storytelling. The movie demonstrates that understanding physics makes personal relationships more poignant, that cosmic scales amplify intimate feelings, and that scientific truth can serve human truth when filmmakers commit to both intellectual rigor and emotional authenticity. The father-daughter relationship between Cooper and Murph serves as the emotional anchor that gives cosmic significance to abstract physics concepts. Their separation across space and time through gravitational effects creates stakes that emerge directly from Einstein's relativity, making the science personally meaningful while making the emotions cosmically significant. Time dilation effects transform the universal experience of parent-child aging into a profound meditation on mortality, memory, and love across temporal scales. When Cooper returns from Miller's planet to find that Ramilly has aged 23 years, the movie demonstrates how physics can create emotional scenarios impossible in everyday life. The watch that Cooper leaves with young Murph becomes a powerful symbol that connects quantum mechanics to family bonds, showing how objects can carry information and emotional meaning across dimensional boundaries. The watch serves both as a plot device for transmitting quantum data and as an emotional connection spanning decades. Scientific sacrifice and personal cost permeate every character's journey. From Dr. Mann's isolation-induced madness to Dr. Brand's choice between love and mission objectives, the movie shows how scientific exploration demands personal prices that test human psychology and relationships in extreme ways. Parental love as a driving force for scientific achievement reflects how personal motivations can inspire cosmic-scale accomplishments. Cooper's determination to return to his daughter motivates him through impossible challenges, suggesting that emotional bonds provide strength for confronting the universe's most extreme phenomena. The evolution of Murph, from angry child to accomplished scientist, demonstrates how personal loss can inspire scientific dedication, or transformation into a physicist working to solve humanity's survival crisis emerges from her relationship with her father and her need to understand the gravitational anomalies affecting their farm. Dr. Brand's emotional struggle between duty and love when choosing between Mann's and Edmund's planets reflects realistic human psychology under extreme stress. Her admission that love might be a force transcending space-time dimensions represents speculation, grounded in emotional rather than scientific reasoning. Communication across cosmic distances creates unique forms of loneliness and connection that the movie explores through realistic treatment of signal delays, resource limitations, and the psychology of isolation. Characters must cope with communication delays measured in years and the knowledge that loved ones are aging in their absence. Scientific ethics and moral decision-making under extreme circumstances force characters to choose between competing values like truth versus hope, individual versus species survival, and scientific integrity versus emotional comfort. Dr. Mann's deception about his planet's habitability represents the psychological pressure of isolation and failure. Team dynamics during long-duration space missions reflect realistic understanding of group psychology, leadership challenges, and interpersonal conflict resolution in high-stress environments. The movie shows how scientific training and personal character interact under conditions where human error can have catastrophic consequences. Grief and loss processing in isolation creates unique psychological challenges for space explorers who must cope with trauma while maintaining mission focus. The movie explores how characters deal with colleague deaths, separation from loved ones, and the possibility that Earth might not survive their mission. Hope and desperation balance throughout the movie as characters confront seemingly impossible odds while maintaining dedication to human survival. This psychological realism reflects how actual explorers and researchers must persist through setbacks and maintain optimism despite overwhelming challenges. Intergenerational responsibility themes connect personal family relationships to species-wide survival concerns. Cooper's obligation to his children becomes symbolic of humanity's obligation to future generations, making scientific achievement a form of parental care extended across cosmic scales. Educational transmission between generations appears in Murph's development from farm child to leading physicist, showing how scientific knowledge passes from parent to child through inspiration, education, and shared commitment to understanding. Their relationship models how scientific passion can be nurtured and transmitted. Love as information processing reflects the movie's speculation that emotional bonds might have physical reality beyond biochemical brain states. Dr. Brand's hypothesis that love transcends space-time dimensions suggests emotional connections might involve quantum or Gravitational phenomena beyond current. Understanding. Sacrifice and heroism redefined through scientific achievement rather than violent action. Represents a sophisticated view of courage that values intellectual bravery and dedication to knowledge. Characters become heroic through scientific problem-solving, exploration, and commitment to truth rather than through combat or conquest. Trust and betrayal in scientific collaboration reflect realistic concerns about research integrity, data sharing, and cooperation under pressure. Dr. Mann's falsification of data represents how psychological pressure can compromise scientific honesty with potentially catastrophic consequences. Individual versus collective survival. Priorities force characters to choose between personal desires and species needs, reflecting ethical dilemmas that arise in extreme situations where individual and group interests conflict. These choices reveal character, while exploring moral philosophy. Cultural preservation through scientific achievement appears in humanity's effort to maintain civilization and knowledge during environmental collapse. The movie suggests that scientific understanding represents essential cultural heritage that must be preserved for future generations. Aging and mortality. Awareness heightened by time dilation effects makes characters more conscious of life's finite nature and the precious value of time spent with loved ones. This awareness adds urgency to personal relationships, while making scientific achievements more meaningful. Mental health challenges during long isolation missions reflect realistic psychological concerns about space travel, including depression, anxiety, social isolation, and the psychological pressure of enormous responsibility for human survival. Communication breakdown and repair between family members separated by space and time demonstrates how relationships must adapt to extraordinary circumstances. Cooper and Murph's relationship evolves through misunderstanding, anger, and eventual reconciliation that spans decades. Scientific curiosity, as human trait, connects intellectual exploration to emotional fulfillment, suggesting that the drive to understand the universe represents fundamental human nature rather than mere intellectual exercise. Characters find meaning through discovery and understanding, forgiveness and reconciliation. Themes appear as characters overcome past hurts and misunderstandings to work together for human survival. The movie shows how extreme circumstances can help people transcend personal grievances and focus on shared values. Legacy and continuity concerns motivate characters to ensure their work survives even if they don't, reflecting how scientific achievement creates forms of immortality through knowledge transmission and cultural impact. The human elements in Interstellar demonstrate that scientific accuracy can serve emotional storytelling by creating authentic stakes, meaningful choices, and profound connections between personal and cosmic scales. The movie proves that understanding physics can make human relationships more rather than less significant. This integration of science and emotion shows how cosmic perspectives can amplify rather than diminish human concerns, making love and family relationships more precious by placing them against the vast scales of space and time revealed through scientific understanding. The success of Interstellar's human elements proves that audiences hunger for stories that respect both scientific truth and emotional truth, showing that intellectual rigor and emotional authenticity can reinforce rather than contradict each other in sophisticated storytelling. Understanding how Interstellar balances science and emotion reveals why the movie resonates so powerfully with audiences. It shows that scientific understanding makes human experiences more meaningful rather than less significant. creating emotional stakes that emerge from cosmic truth rather than opposing it. Chapter 9. Visual Accuracy. The visual effects in Interstellar represent a revolutionary approach to science fiction filmmaking, where computer graphics followed physics equations rather than artistic imagination, creating images so scientifically accurate. They advanced actual research while proving that realistic physics can produce more spectacular visuals than pure fantasy. This commitment to visual accuracy required developing new computational techniques, consulting with leading physicists, and solving mathematical equations to determine what impossible scenarios would actually look like. The creation of Gargantua, Interstellar's massive black hole, required solving Einstein's general relativity equations to determine exactly how light would behave in extreme gravitational fields. Visual effects supervisor Paul Franklin worked directly with Kip Thorne to develop new ray tracing software that could simulate millions of light paths through curved spacetime to create physically accurate black hole imagery. Gravitational lensing. Effects around Gargantua revealed visual phenomena that surprised even the physicists involved in the project. The black hole's gravitational field bends light so dramatically that multiple images of the accretion disk appear above, below, and around the black hole's shadow, creating visual complexity that emerges from pure physics rather than artistic design. The accretion disk surrounding Gargantua demonstrates sophisticated understanding of plasma physics, magnetic field dynamics, and relativistic fluid flow. The disk's structure, color gradients, and brightness variations reflect real physics of how matter behaves in extreme gravitational and magnetic field environments. Doppler shifting effects in the rotating accretion disk create realistic asymmetric brightness patterns where material moving toward observers appears brighter and bluer, while material moving away appears dimmer and redder. These relativistic effects create the characteristic appearance of rotating black holes that has since been confirmed by real black hole observations. Frame dragging effects from Gargantua's rotation influence how light propagates near the black hole, creating subtle but important modifications to the gravitational lensing patterns. These effects demonstrate sophisticated understanding of rotating black hole spacetime geometry and its effects on electromagnetic radiation. The tesseract construction required visualizing theoretical concepts from higher dimensional physics and general relativity. The filmmakers consulted theoretical physicists and mathematicians to create representations of five-dimensional space and time navigation that remained consistent with serious theoretical speculation about extra-dimensional physics. Wormhole visualization techniques involved solving general relativity equations for traversable wormholes, creating the first accurate moving images of how these hypothetical space-time shortcuts would appear to travelers passing through them. The distinctive spherical appearance and visual distortion effects reflect mathematical predictions from wormhole physics. Spacecraft engineering design incorporated realistic orbital mechanics, propulsion physics, and life support requirements. Every spacecraft component, from the Endurance's rotating sections to the Ranger's atmospheric flight capabilities, reflects consideration of actual engineering constraints and space technology limitations. Planetary environment accuracy extended beyond visual appearance to include atmospheric physics, geological processes, and climate dynamics. Miller's planet's massive waves reflect realistic tidal effects from Gargantua's gravity, while Man's ice planet shows plausible atmospheric composition and weather patterns. Dust storm visualization on Earth demonstrates sophisticated fluid dynamic simulation and particle transport physics. The massive dust clouds affecting the American Midwest reflect realistic atmospheric dynamics and particle behavior during severe dust storm events. Lighting and optical effects throughout the movie maintain consistency with realistic physics of light propagation, atmospheric scattering, and optical phenomena in different environments. Sky colors, visibility conditions, and lighting characteristics reflect accurate physics of how different atmospheric compositions and lighting conditions would appear. Space environment. Rendering eliminates sound effects during space sequences and shows realistic spacecraft behavior in vacuum conditions. The absence of atmospheric effects and the stark contrast between illuminated and shadowed regions reflect accurate understanding of space environment conditions. Time dilation visual effects demonstrate sophisticated temporal manipulation techniques that maintain continuity and logical consistency during sequences where different characters experience time at different rates. These effects required careful planning to show realistic consequences of relativistic time effects. Computer graphics innovation for Interstellar included developing new rendering techniques for extreme gravitational lensing, higher dimensional visualization, and complex particle dynamics. These technological developments advanced computer graphics capabilities while serving scientific accuracy rather than pure spectacle. Practical effects integration combined realistic sets, locations, and physical props with computer-generated environments to create seamless blending between real and simulated elements. The massive cornfields, rotating spacecraft interiors, and practical dust effects ground fantastic elements in physical reality. Color grading and visual tone throughout the movie reflect realistic lighting conditions and atmospheric properties in different environments. The warm golden tones of Earth's dusty atmosphere contrast with the harsh lighting of space environments and the unique optical properties of alien worlds. Scale and proportion accuracy ensures that astronomical objects, spacecraft, and planetary features maintain realistic size relationships. The enormous scale of Gargantua, compared to nearby spacecraft and planets, reflects accurate understanding of supermassive black hole dimensions. Motion and dynamic simulation for spacecraft maneuvering, orbital mechanics, and atmospheric flight incorporate realistic physics of acceleration, rotation, and gravitational effects. Vehicle movements reflect authentic space physics rather than atmospheric flight dynamics. Particle system simulation for dust storms, atmospheric effects, and accretion disk dynamics involves complex fluid dynamics calculations and realistic particle behavior under different gravitational and electromagnetic conditions. Texture and surface detail work on planetary environments, spacecraft surfaces, and equipment reflects realistic material properties, weathering effects, and environmental adaptation. Surface characteristics reflect plausible engineering solutions and environmental wear patterns. Atmospheric and environmental effects simulation includes realistic treatment of atmospheric scattering, cloud formation, precipitation patterns, and visibility conditions under different atmospheric compositions and pressure regimes. Mathematical visualization techniques transform abstract physics equations into compelling visual imagery that maintains scientific accuracy while remaining accessible to general audiences. Complex mathematical relationships become visible through sophisticated computer graphics techniques. Research collaboration between visual effects, artists, and working physicists created new standards for scientific accuracy in computer graphics, while demonstrating how artistic and scientific communities can collaborate productively to achieve shared goals. Software development for Interstellar's visual effects involved creating new computational tools for relativistic ray tracing, gravitational lensing simulation, and higher dimensional visualization that have since been used by other research and entertainment projects. Quality control and accuracy verification involved frame-by-frame review of visual effects sequences by physicists to ensure that every visual element remained consistent with known physics principles and theoretical speculation based on serious scientific research. Educational impact of Interstellar's visual accuracy extends through university physics courses, planetarium shows, and science communication efforts that use movie imagery to explain complex physics concepts to students and general audiences. Industry influence from Interstellar's approach to visual effects has encouraged other filmmakers to prioritize scientific accuracy in science fiction projects, while demonstrating that realistic physics can enhance rather than constrain visual creativity. Future applications of visualization techniques developed for Interstellar include scientific research tools, educational software, and advanced computer graphics applications that benefit from the mathematical and computational innovations created for the movie. The visual accuracy achievement in Interstellar demonstrates that scientific realism can produce more spectacular and memorable imagery than pure fantasy when filmmakers commit to understanding and depicting the genuine beauty and complexity of physical reality. This approach to visual effects proves that audiences respond powerfully to authentic scientific visualization, suggesting that future science fiction filmmaking might increasingly emphasize accuracy and realism as sources of visual inspiration rather than obstacles to overcome. The revolutionary visual accuracy of Interstellar establishes new standards for scientific visualization in entertainment, while contributing to scientific understanding through computational techniques that advance both artistic and research capabilities simultaneously. Chapter 10: Ultimate Legacy. Interstellar's legacy extends far beyond entertainment into education, scientific research, and cultural transformation, proving that scientifically accurate filmmaking can inspire real scientific progress while changing public perception of science fiction's potential for serious intellectual engagement. The movie has fundamentally altered how audiences and filmmakers approach the relationship between scientific truth and creative storytelling, establishing new standards for accuracy that influence projects across entertainment and education. Educational transformation represents perhaps Interstellar's most significant legacy, with physics professors worldwide incorporating movie scenes into relativity lectures, astronomy courses, and general science education. Dr. Neil deGrasse Tyson, Dr. Brian Cox, and countless other science educators have praised the movie's accuracy and used its visualizations to explain complex concepts to students and general audiences. University physics departments report increased enrollment in theoretical physics and astrophysics courses following Interstellar's release, with many students citing the movie as inspiration for pursuing careers in physics, astronomy, and space exploration. The movie demonstrates that accurate science can be as exciting as any fantasy, inspiring new generations of researchers. NASA's educational outreach programs have incorporated interstellar clips and concepts into presentations about black holes, space exploration, and planetary science. The agency's scientists regularly reference the movie during public lectures and educational events, validating its scientific accuracy while using its popularity to engage broader audiences. Scientific research contributions from Interstellar include peer-reviewed publications about black hole visualization, gravitational lensing effects, and computational techniques for relativistic ray tracing. The movie's black hole imagery has been cited in astrophysics literature and used as reference material for understanding how real black holes might appear to human observers. The Event Horizon Telescope collaboration that produced the first real black hole image in 2019 used computational techniques similar to those developed for Interstellar, validating the movie's visualization approach while demonstrating how entertainment projects can contribute to actual scientific research capabilities. Public science communication has been transformed by Interstellar's example, showing how complex physics concepts can be made accessible through compelling storytelling and accurate visualization. Science communicators now reference the movie as a model for engaging general audiences with sophisticated scientific concepts. Kip Thorne's book, The Science of Interstellar, became an international bestseller, demonstrating public appetite for understanding the real physics behind science fiction narratives. The book's success has encouraged other scientists to write accessible explanations of their research for general audiences. Gravitational wave astronomy benefited from increased public interest following Interstellar's accurate depiction of space-time distortion and black hole physics. When LIGO detected gravitational waves in 2015, the public was better prepared to understand the significance of the discovery, partly due to concepts popularized by the movie. Hollywood's approach to science fiction has been influenced by Interstellar's success, with subsequent projects showing increased attention to scientific accuracy and consultation with working scientists. The movie proved that audiences appreciate and respond to authentic scientific content when it serves compelling human stories. Space exploration advocacy has been strengthened by Interstellar's portrayal of interstellar travel as scientifically plausible rather than pure fantasy. The movie provides realistic scenarios for space exploration that help build public support for space research and exploration programs. Climate change awareness has been enhanced by the movie's accurate depiction of agricultural collapse and environmental crisis, showing how environmental challenges could motivate space exploration, while emphasizing the importance of planetary stewardship and environmental protection. International space cooperation has been inspired by Interstellar's vision of humanity working together for species survival through scientific achievement. The movie provides compelling narratives for international collaboration on space, exploration, and scientific research projects. STEM education initiatives worldwide have used Interstellar as a recruitment and inspiration tool, showing students that scientific careers can involve adventure, discovery, and meaningful contribution to human knowledge and survival. The movie has helped counteract stereotypes about science as boring or irrelevant. Research funding and public support for theoretical physics research has benefited from increased public understanding of concepts like black holes, gravitational waves, and relativity theory popularized by Interstellar. The movie helps justify public investment in fundamental research by showing its potential applications. Science fiction literature and media have been influenced by Interstellar's approach to hard science fiction, with authors and filmmakers increasingly emphasizing scientific accuracy and consultation with working scientists. The movie has raised expectations for scientific authenticity in speculative fiction. Museum and planetarium programs worldwide have developed exhibits and shows based on Interstellar's scientific concepts, using the movie's popularity to attract visitors while educating them about real physics and astronomy. These programs demonstrate lasting educational value beyond the movie's initial release. Academic conferences in both physics and film studies have featured sessions analyzing Interstellar's scientific accuracy and cultural impact, examining how entertainment can serve scientific education while maintaining artistic integrity. The movie has become a case study in science communication. International scientific collaboration has been inspired by Interstellar's portrayal of global cooperation for species survival, providing narratives that support international research partnerships and shared scientific goals that transcend national boundaries. Technology development in visualization and computational physics has benefited from techniques developed for Interstellar's visual effects, with applications extending beyond entertainment into scientific research, educational software, and advanced computer graphics development. Cultural perception of scientists and scientific work has been influenced by Interstellar's portrayal of physicists and explorers as heroes whose intellectual courage saves humanity. The movie counters anti-intellectual trends by showing scientific understanding as essential for human survival and flourishing. Future mission planning for space exploration increasingly references concepts from Interstellar, with NASA and other space agencies studying the movie's technical elements for insights into long-duration space travel, interstellar mission architecture, and human factors in extreme environments. Philosophical discussions about time, consciousness, and human relationships have been enriched by Interstellar's exploration of how scientific understanding affects personal meaning and emotional experience. The movie demonstrates that scientific truth enhances rather than diminishes human significance. Climate science communication has been improved by Interstellar's realistic depiction of environmental crisis and agricultural collapse, providing compelling scenarios that help audiences understand potential consequences of environmental degradation while motivating support for environmental protection. The democratization of scientific knowledge has been advanced by Interstellar's proof that general audiences can understand and appreciate complex physics when it's presented through engaging storytelling and accurate visualization. This challenges assumptions about public scientific literacy and interest. Long-term cultural impact of Interstellar continues to unfold as students inspired by the movie enter scientific careers, as researchers use its visualization techniques for new discoveries, and as its accurate science continues to educate audiences through streaming platforms and educational use. The measurement of Interstellar's success extends beyond box office returns to include scientific citations, educational applications, and cultural influence on public understanding of physics and space exploration. These metrics demonstrate that accuracy can enhance rather than constrain commercial and artistic success. Future implications of Interstellar's legacy include the possibility that scientifically accurate entertainment could become a standard expectation rather than unusual achievement, transforming how stories about science and technology are told across all media platforms. The ultimate legacy of Interstellar lies in proving that scientific truth and human truth can reinforce rather than oppose each other, that understanding physics makes life more meaningful rather than less significant, and that accurate science can inspire hope, wonder, and determination to face cosmic challenges through human intelligence and cooperation. This legacy transforms Interstellar from a movie into a cultural phenomenon that demonstrates the power of scientific understanding to inspire human achievement while showing that rigorous accuracy serves rather than constrains creative storytelling about humanity's cosmic destiny. The enduring significance of Interstellar's achievement lies not just in what it accomplished, but in what it proved possible, that entertainment can educate, that accuracy can inspire, and that understanding the universe through science makes human life more rather than less meaningful in the cosmic story of existence. The transformative influence of Interstellar's scientific accuracy extends into emerging fields and technologies that didn't exist when the movie was released, demonstrating how prescient scientific storytelling can anticipate and inspire future developments. The movie's rigorous approach to physics has become a touchstone for evaluating scientific authenticity in media, creating new standards that influence everything from streaming documentaries to virtual reality experiences. Artificial intelligence and machine learning applications have begun incorporating visualization techniques pioneered for Interstellar's black hole sequences. Dr. Katie Bouman's team, which produced the Event Horizon Telescope's first black hole image, explicitly credited the movie's computational approaches as influential in developing their image reconstruction algorithms. This represents a direct pipeline from entertainment technology to groundbreaking scientific discovery. Virtual and augmented reality educational platforms now use Interstellar's scientific frameworks to create immersive physics experiences. Students can virtually experience time dilation effects, navigate through Gargantua's accretion disk, and explore the Tesseract's higher dimensional geometry through VR, applications that maintain the movie's commitment to scientific accuracy while providing hands-on learning opportunities. The gaming industry has been particularly influenced by Interstellar's realistic approach to space physics, with multiple space simulation games adopting accurate orbital mechanics, realistic time dilation effects, and scientifically grounded space travel scenarios. Games like Kerbal Space Program and Elite Dangerous have incorporated physics, concepts popularized by Interstellar while maintaining playability. Social media science communication has been revolutionized by content creators who use interstellar references and visualizations to explain complex physics concepts to millions of followers. YouTube channels, TikTok accounts, and Instagram pages regularly reference the movie when discussing black holes, relativity, and space exploration, creating viral educational content that reaches audiences far beyond traditional academic settings. Corporate space industry development has been inspired by Interstellar's realistic depiction of space travel challenges and solutions. SpaceX engineers have cited the movie's treatment of long-duration space travel, artificial gravity generation, and interplanetary mission architecture as influential in their approach to Mars mission planning and spacecraft design philosophy. International space policy discussions increasingly reference scenarios from Interstellar when considering planetary defense strategies, backup civilization planning, and international cooperation frameworks for species-threatening emergencies. The movie provides compelling narratives for understanding why space exploration represents essential insurance for human civilization. Crowdfunding and public support for space research projects often invoke Interstellar's themes and scientific concepts when appealing to donors and supporters. The movie's emotional connection between scientific achievement and human survival creates powerful messaging for research, funding campaigns, and public science advocacy efforts. Science museum exhibit design has been transformed by Interstellar's approach to making abstract physics concepts tangible and emotionally engaging. Museums worldwide have developed black hole simulators, time dilation demonstrations, and gravitational wave detectors inspired by the movie's visualization techniques and educational philosophy. Online education platforms and massive open online courses MOOCs frequently use interstellar clips and concepts to introduce physics topics, with professors reporting increased student engagement when complex concepts are connected to the movie's familiar scenarios. The movie serves as a common cultural reference point that makes advanced physics more accessible. Mental health applications have emerged from Interstellar's exploration of isolation, family separation, and psychological challenges during extreme circumstances. Researchers studying long-duration space travel psychology use the movie's realistic treatment of separation anxiety, decision-making under stress, and maintaining hope during seemingly impossible situations. Climate change advocacy has been strengthened by Interstellar's realistic depiction of environmental collapse and its consequences for human civilization. Environmental organizations use the movie's agricultural crisis scenarios to illustrate potential consequences of current environmental trends while advocating for planetary stewardship and sustainable development. Scientific visualization software development has incorporated ray tracing techniques and rendering algorithms originally developed for Interstellar's visual effects. These tools now serve research applications in astrophysics, computational physics, and scientific modeling that require accurate representation of extreme physical phenomena. Philosophical discourse about consciousness, free will, and determinism has been enriched by Interstellar's exploration of higher dimensional physics and time manipulation. Academic conferences in philosophy of mind regularly reference the movie when discussing questions about consciousness's relationship to physical reality and temporal experience. Religious and spiritual communities have engaged with Interstellar's themes about transcendence, sacrifice, and cosmic purpose, finding in the movie's scientific accuracy a foundation for discussing relationships between scientific understanding and spiritual meaning. The movie provides common ground for science-religion dialogue that respects both domains. Professional development in science communication now includes training modules based on Interstellar's successful integration of complex physics with emotional storytelling. Scientists learning to communicate with public audiences study the movie's techniques for making abstract concepts personally relevant and emotionally compelling. Therapeutic applications have emerged from Interstellar's treatment of grief, separation, and family relationships across time and space. Family therapists report using the movie's themes to help clients process loss, understand intergenerational relationships, and find meaning during difficult transitions and separations. Investment and venture capital decisions in space technology companies increasingly reference Interstellar's realistic scenarios when evaluating business models and technological feasibility. The movie provides frameworks for understanding which space technologies might prove commercially viable versus purely speculative ventures. Literary criticism and science fiction studies have established Interstellar as a landmark work that redefined the relationship between scientific accuracy and narrative sophistication in speculative fiction. Academic courses on science fiction now use the movie as a case, studying how rigorous science can enhance rather than constrain creative storytelling. Aerospace engineering curriculum development has incorporated lessons from Interstellar's treatment of spacecraft design, mission planning, and human factors in extreme environments. Engineering schools report increased student interest in space-related careers, following exposure to the movie's realistic technical challenges and solutions. Public policy formation around emerging technologies like genetic engineering, artificial intelligence, and space resource utilization increasingly references ethical frameworks inspired by Interstellar's treatment of difficult choices under extreme circumstances. The movie provides case studies for understanding how scientific capabilities create new moral responsibilities. Disaster preparedness and resilience planning have been influenced by Interstellar's scenarios about species-threatening emergencies and backup civilization strategies. Emergency management professionals study the movie's treatment of resource allocation, population prioritization, and long-term survival planning during existential threats. Collaborative research methodologies have been inspired by Interstellar's portrayal of international scientific cooperation during crisis situations. Research institutions increasingly emphasize global collaboration frameworks that mirror the movie's depiction of scientists working together for species survival rather than national advantage. Scientific instrument design has been influenced by Interstellar's accurate depiction of measurement challenges in extreme environments. Gravitational wave detector improvements, black hole imaging techniques, and space-based observatory designs incorporate lessons from the movie's treatment of precision measurement under challenging conditions. Cultural bridge building between scientific and artistic communities has been facilitated by Interstellar's example of successful collaboration between filmmakers and researchers. Arts councils and science funding agencies now actively promote interdisciplinary projects that combine scientific accuracy with artistic expression. Future mission architecture for interstellar exploration increasingly references concepts from Interstellar when considering generational ships, closed-loop life support systems, and psychological challenges of multi-decade space travel. The movie provides realistic frameworks for understanding human factors in extreme exploration scenarios. The democratization of scientific knowledge continues advancing through Interstellar's proof that general audiences can appreciate sophisticated physics when presented through compelling narratives. This challenges traditional assumptions about scientific communication and opens new possibilities for public engagement with complex research. Legacy preservation efforts in science communication now study Interstellar's techniques for creating lasting cultural impact through accurate scientific content. The movie demonstrates that rigorous science can achieve broad cultural penetration and long-term influence when combined with skillful storytelling and emotional authenticity. Emerging technologies like quantum computing and artificial general intelligence increasingly reference Interstellar's treatment of the higher dimensional physics and consciousness technology interactions when considering implications for human understanding and capability enhancement. These expanding applications demonstrate that Interstellar's ultimate legacy lies not just in what it achieved, but in what it proved possible about the relationship between scientific truth and human meaning. The movie continues generating new applications and inspiring new approaches to science communication, education, and cultural engagement that respect both intellectual rigor and emotional authenticity. The ongoing influence reveals that accuracy and accessibility are not opposing forces, but complementary aspects of effective science communication that can serve both educational and entertainment goals simultaneously. Interstellar established that understanding real science makes fictional scenarios more rather than less compelling, creating new possibilities for how human knowledge and creativity can reinforce each other. As virtual reality, artificial intelligence, and space exploration continue developing, Interstellar's scientific frameworks provide validated approaches for maintaining accuracy while maximizing public engagement and educational impact. The movie's legacy suggests that future science communication might increasingly emphasize rigorous accuracy as a source of wonder rather than an obstacle to overcome. This extended impact demonstrates that Interstellar achieved something unprecedented in science communication, creating a cultural work that simultaneously entertains, educates, and inspires while maintaining scientific integrity and emotional authenticity. The movie proves that when science and storytelling collaborate effectively, the results can exceed what either domain could accomplish independently, creating lasting cultural value that serves both human knowledge and human meaning. The revolution continues as new generations of scientists, filmmakers, educators, and communicators build upon Interstellar's foundation, proving that the movie's greatest achievement was not just depicting accurate science, but demonstrating how accuracy itself can become a source of infinite creativity and inspiration. Throughout this exploration of Interstellar's unprecedented scientific accuracy, we've discovered that this movie represents far more than entertainment. It's a revolutionary demonstration that understanding real physics makes impossible scenarios feel achievable, that scientific truth enhances rather than constrains creative storytelling, and that audiences hunger for authentic intellectual engagement when it's woven through compelling human drama. Interstellar succeeded where countless other space movies failed because it started with real science and built impossible dreams on possible physics. From Gargantua's gravitational lensing to Miller's planet time dilation, from accurate orbital mechanics to realistic agricultural collapse, every element emerged from consultation with working scientists who ensured that fantasy remained grounded in mathematical reality. The collaboration between Christopher Nolan and Kip Thorne created a new model for how science and storytelling can enhance each other, rather than treating scientific accuracy as an obstacle to overcome. They used physics constraints as creative opportunities that led to more innovative and emotionally powerful scenarios than conventional science fiction approaches. But perhaps the most remarkable discovery is how scientific understanding made every human moment more meaningful. Cooper's aging while Murph grows old derives its emotional power directly from Einstein's equations. The Tesseract sequence gains profundity through theoretical physics rather than magical thinking. Love becomes more precious when viewed against cosmic scales revealed through scientific truth. The movie's legacy continues expanding as students inspired by its scientific accuracy enter physics careers, as researchers use its visualization techniques for discoveries, and as educators worldwide incorporate its scenes into science curricula. Interstellar proved that getting the science right doesn't limit storytelling. It transforms imagination into inspiration. When you look up at the night sky now, knowing that black holes like Gargantua really exist and behave exactly as the movie depicted, you're seeing the universe through scientifically educated eyes. Understanding that time dilation actually occurs near massive objects, that gravitational waves really ripple through space-time, and that interstellar travel follows discoverable physical laws makes cosmic reality more amazing than any fiction. The most profound lesson from Interstellar's scientific accuracy is that we live in a universe governed by mathematical principles so elegant and beautiful, they surpass human imagination. Reality follows equations more spectacular than fantasy, operates through mechanisms more creative than magic, and offers possibilities more inspiring than pure speculation. As you continue through your daily life after understanding why Interstellar represents cinema's most accurate science, remember that the same physical laws governing black hole mergers and time dilation also operate in your immediate environment. Every moment of your existence participates in cosmic processes described by Einstein's theories and quantum mechanics. If you're inspired by how scientific accuracy can enhance rather than constrain creative storytelling, subscribe and hit thumbs up for more explorations of how understanding real physics makes everything more meaningful. Check out my video on what really happens inside a black hole, where we explore the science behind Cooper's journey into Gargantua. The question we began with, why Interstellar is the most accurate space movie ever made, has revealed itself as an exploration of how scientific truth and human meaning reinforce each other. The movie succeeds because it shows that understanding cosmic reality makes human experiences more significant rather than less important. Interstellar's ultimate achievement lies in proving that accuracy and wonder are partners rather than opponents, that learning physics enhances appreciation for existence rather than diminishing it, and that scientific understanding provides the most solid foundation for hope about humanity's cosmic future. When we truly understand the science behind Interstellar, we realize that living in a universe governed by Einstein's relativity and quantum mechanics is far more inspiring than inhabiting any fictional cosmos. Reality surpasses imagination when we comprehend it clearly enough to appreciate its mathematical beauty and creative potential. The most accurate space movie ever made reveals that accuracy itself makes space more wondrous, physics more poetic, and human consciousness more miraculous for existing within cosmic processes that follow discoverable laws while generating unlimited creativity and beauty through scientific truth. Every time you watch Interstellar now, you'll experience it differently, not as impossible fantasy, but as plausible future, not as science fiction, but as science education, not as entertainment alone, but as inspiration for understanding the magnificent universe we actually inhabit. The movie's greatest gift isn't just showing us spectacular cosmic scenarios, but teaching us that the real universe is more spectacular than any fictional creation. Understanding the science behind Interstellar means understanding that we live within the most amazing story ever told. The story of cosmic evolution, scientific discovery, and conscious beings capable of comprehending their own cosmic context. This is why Interstellar stands alone as cinema's most scientifically accurate space epic. It proves that when we get the science right, everything else becomes more meaningful, more beautiful, and more inspiring. The universe doesn't need fiction to be amazing. It just needs us to understand it well enough to appreciate the incredible reality we're privileged to experience. The legacy of Interstellar's accuracy will continue inspiring future filmmakers, scientists, and dreamers to build impossible dreams on possible science, proving that the best science fiction emerges when we take science seriously enough to discover that reality exceeds our wildest imagination.